Hello and welcome to the webinar, Demystifying Spatial Resolution of Fizeau Interferometers. We'll just give another half minute here or so for folks to file in. Maybe take a few minutes to work with the GoToWebinar interface. You can resize and adjust the size of screens. You can make the slideshow a little bit bigger and adjust the size of the live video feed. I'll be switching to a live demonstration here where it might be helpful to be able to adjust the size of one or the other of the presentation material. All right, we'll get started. My name is Tyler Steele. I'm the product manager for laser interferometers at Zygo. I'm based out of our Tucson, Arizona office. And joining me today for Q&A are two of our senior applications engineers, Eddie Lavilla out of our headquarters in Middlefield, Connecticut, and also Mackenzie Massey out of our Santa Clara, California office. So if any questions come up, if you have a question during the webinar, feel free to type it into the chat function there and go to webinar. And Eddie or Mackenzie will try to respond to you. And we'll answer a few questions during the webinar. We'll take a break in the middle and have some questions at the end also. So in the webinar, we'll talk about concepts regarding spatial resolution, also known as lateral resolution. I'll use those terms sort of interchangeably throughout the presentation. We'll describe surfaces by their spatial frequency content and bring some order to how to describe a surface itself. We'll talk about the instrument transfer function and its impact on metrology. Also, how to quantify the ITF of an interferometer, along with a live demonstration of how we do that. And we'll answer the question, what does one do with ITF information once you've qualified an interferometer? What do we do with ITF? And we'll explore a few of the options for high resolution interferometry from Zygo. So to start, what does lateral resolution mean? What does this spatial resolution even mean? And a common thought process is something like, my interferometer has a 100mm aperture. I've got 1,000 pixels across the aperture. That means I should be able to resolve features that are 0.1mm in size. Let's explore that. So if we have our interferometer, 1,000 pixels across the aperture, that means each pixel is 0.1mm in size. And it stands to reason that we should be able to apply those pixels to a surface and be able to resolve features that are on the order of the size of the pixel. And to first order, this is true. The answer is yes. This is the resolving limit of a phase measuring interferometer, the Nyquist limit. But if that was the end of the story, this would be a pretty boring webinar. So there's more to talk about. So in optical surface metrology, it's less common to want to measure individual small features. Rather, the overall form and features over an entire surface are typically of interest. One of the reasons for that, small tool deterministic polishing has expanded greatly in recent years. It's extremely efficient in polishing, but the trade-off is it often leaves some structure, some unwanted information in the surface. So how do we define resolution, the resolution required to characterize these kinds of surfaces? And how do we even characterize the surface itself? So first, let's investigate how we can describe the surface itself. So in this case, let's assume we have an actual physical surface here, not necessarily the measured surface, but we'll pretend that this is the actual surface for just a moment, and I'll talk about why the difference between the actual surface and the measured surface in just a little bit. So if we'll talk through some concepts here. If we start with just a 2D profile of the surface to investigate this first concept, starting with the 2D profile of the surface itself, we see this surface is a little bit irregular, and we'd like to bring some order to the surface to be able to describe it. So one of the ways we can do that is to apply a Fourier transform. And if we remember back to our high school physics class, a Fourier transform will break a signal like this down into its individual component sinusoidal elements. And each component has a particular magnitude, and each component has a particular period that is unique, but it's also constant for each component. However, component surface information, as we just described, it's not discrete, although particular components can dominate the surface information. It's actually a full spectrum of components or frequencies that exist in a surface. And this spectrum defines, in this case, the spatial frequency content of a surface. So let's revisit the mirror surface we started with and try to describe some of these features. We'll start again here with the physical surface, the actual surface, theoretically. And in this case, we've got the 2D surface. So now we'll do a 2D Fourier transform in order to get the spatial frequency content of the entire surface, with low spatial frequencies on the left and high spatial frequencies on the right. And if we investigate just a portion of the spatial frequency content, let's start with the low spatial frequency information. And now we can do an inverse Fourier transform, which will bring us from the frequency domain back into the spatial domain, the surface domain. And we see that the low spatial frequency content in the surface domain gives us very slowly varying surface information. This is the lower spatial frequency, what we typically call form, which is typically less than 10 cycles per aperture, roughly speaking, in terms of variation. It's the slowly varying information. And if we look now at the middle portion of the spatial frequency band, and again we do an inverse Fourier transform, we see much more quickly varying information, smaller features. Here we would typically call this mid-spatial frequency content. These are features that are typically tens of cycles up to hundreds of cycles per aperture. And interrogating the far right end, or the highest spatial frequency portion of the spectrum, we see that in the spatial domain, the features are much, much smaller laterally. They're also much smaller in magnitude. And this is typically the roughness content of a surface, the highest spatial frequency information. So these are features that are smaller than interferometer sampling, typically less than 10 micrometer periods, something that would be much smaller than can be resolved by an interferometer. This is the reason that I wanted to start with the physical surface, not necessarily say that this is the measured surface, although it is actually a measurement. Conceptually, if we think about it as a theoretical physical surface, all of these spatial frequencies exist in a physical surface. So this is a bit of a wall of words. I apologize, but stick with me for just a moment because this part is important. So we've described surface characteristics in great detail, but how does an interferometer see those surfaces, and what does resolution mean in that context? Well, an interferometer will see, or more appropriately, transfer surface information as a function of spatial frequency, where lower spatial frequencies are transferred more reliably and higher spatial frequencies are transferred less reliably. And this phenomenon is known as the instrument transfer function, or ITF, and it can significantly affect how surface information is gathered and communicated. The ITF is a function of the optical design of the instrument itself, its quality of manufacture, and even the camera sensor itself play a role in the ITF of the interferometer. In this discussion, I won't get into the derivation of why ITF occurs and sort of the gory details and the math behind the scenes. There's lots of resources out in the public domain that if anyone is interested can be dug into. I've listed a few of those sources here. They can be found right on the Zygo website with no credentials needed. For this talk, we're going to stick mostly with an application level and talk about how ITF can affect measurements for the end user and what can be done to deal with that and try to understand it a little bit. Okay, so we agree that the ITF affects measured surface information, and we said that lower spatial frequencies are transferred more reliably and higher spatial frequencies are transferred less reliably. A more specific way to say that is that lower spatial frequencies are measured at or near their true physical height, and higher spatial frequencies are measured lower than their true physical height. And that's nice to talk about, but it would be great if we actually had a surface that we could see this effect. If we had some well-controlled features that were a constant height, but maybe varying in spatial frequency in order to visualize this. And we just happen to have such an artifact. This is what we call a chirped artifact. This is a interferometer measurement of a chirped artifact. The artifact is a step artifact where the substrate is in the dark region here, and the step regions, the higher regions, are 40 nanometers above the substrate. And each of these segments of the artifact have different features etched into them. And in this case, we're looking at the segment here where there are features that are relatively large toward the center, and they get smaller, they get higher in spatial frequency radially out toward the edge. And we see if we interrogate that segment with a profile slice, we can see that the height that's reported near the center, with the larger features, the height is reported at about 40 nanometers, which is the nominal height of the physical steps in the entire artifact. But as the features get smaller and the spatial frequencies get higher, we see that the reported height actually does decrease, and it decreases all the way to 0, where the frequency gets so high that the height reported is actually 0. So a quick sanity check on this artifact. Let's investigate another segment of the artifact that has the same step heights etched into the surface. But in this case, this segment has features that do not vary in spatial frequency. They're a constant frequency, constant size. And they're relatively large, so they should measure at or near their true height. And we see in the profile slice that in fact the height reported for those features is constant. It's about 40 nanometers throughout that profile slice. So we see, you know, in the case where spatial frequency does not change and it's a fairly low spatial frequency, that the height is reported at or near the true height. Okay, so the chirped artifact clearly shows the ITF effect. Measured heights are reported lower than their physical height. But can we use it to quantify interferometer response to all spatial frequencies? That's ultimately what we'd like to do, is to understand how the interferometer responds to all spatial frequencies. In this case, it's difficult to precisely quantify the transfer rate with this type of artifact. It's similar to the subjectivity of something like the Air Force resolution target, where we have not blurry and blurry, but by how much exactly? It's a little bit subjective. And the reasons are there's a non-uniform response as a function of spatial frequency, so fitting a curve or a specific quantity is not straightforward. You can see we've fit a little bit of a line fit here, and we can see that although the spatial frequency does decrease as the reported height does decrease as a function of spatial frequency, it doesn't do so in a uniform way. So it's difficult to fit a specific quantity. There's a field-dependent response that's difficult to capture with such a chirped artifact. And chirped artifacts are quite difficult to manufacture uniformly, and they're even more difficult to clean. So we'd like to have a more general method to quantify ITF, and it turns out that general and precise methods do exist to quantify optical system response. And these are known generally as the optical transfer function, where a step function input into the optical system will result in some edge spread function in the most general definition. Something that's probably familiar to many in the optics industry, imaging systems that transfer intensity information. These are camera lenses, imaging systems. Those can be tested with the MTF, which is the intensity portion of the OTF. An MTF can be tested with an intensity step. So in this case, we have a light to dark step function, intensity step, that's imaged through an imaging system. And what results is some spread of that sharp step. But interferometers don't measure intensity. Interferometers measure phase. So they transfer phase information. The phase transfer function is the phase portion of the OTF. And note that the phase transfer function and ITF are used interchangeably. It's just a matter of terminology. So the ITF can be tested with a phase step, which is just a physical step. So if we start with our step function input, this would, rather than being an intensity step, this is actually a physical step with a low and a high region and a sharp step in between. If we measure that with the interferometer, we should get some response that is spread, and the amount of spread in the measurement of the measured step will tell us directly the ITF of the instrument. So I'll pause here for just a moment and answer a few questions if there have been any.
We do have one question so far, and the question is, early in the presentation, you mentioned the Nyquist limit. What exactly does that mean?
The Nyquist limit in this context just defines the feature size or the frequency that can be sampled with a given sampling density or pixel frequency, if we think about it in frequency domain. So for instance, if pixels occur at a frequency of say 10 pixels per millimeter in object space, the maximum frequency that can be detected on a surface is half of that. It's 5 cycles per millimeter. So it's just the maximum frequency that can be sensed with a particular discrete sensing artifact, such as a camera. All right, we'll press on here. So we've discussed Now, the theory of how to test ITF, how do we do that in the real world? And we say that an ITF can be performed using a precise step height artifact, but there are a few ground rules. And you see we actually have an artifact here. This is a plano piece of glass, polished very flat, and it's mounted in a 4-inch bayonet cell, which is then in a 2-axis mount for alignment to the interferometer. So the first rule here is that the steps should traverse the full field of the aperture, and I have here a phase measurement of the surface of the artifact, and we see that in fact it's actually not a flat piece of glass. There are these steps that are etched into the surface. So there's a horizontal and a vertical step that's etched into the surface. There are also these rectangular features. These are not germane to the ITF measurement itself. They're only there for a focus aid, not necessarily germane to the measurement. But we see that the steps do indeed traverse the full field. The second rule is that the step height should be small relative to the max phase step of the instrument being measured. So if we interrogate a small region of the step artifact, we can draw a profile slice across that region. And we see in this case that the step height is about 30 nanometers, which is quite a bit smaller than the phase step of the instrument, which is on the order of 150 nanometers. And finally, we want to know that the step is sharp relative to the sampling density of the interferometer. It wants to be much smaller than the size of a pixel of the interferometer. So we can interrogate an even smaller region of the step with a scanning white light interferometer. In this case, we're using a 50x objective and a 2x magnification for 100x total magnification. And we draw a profile slice across that step, and we see that the width of the step is less than 3 microns, so extremely sharp. This is a factor of 10 smaller than even the highest resolution Fizeau interferometer. So we think we have a very sharp step edge here also. Okay, so we've identified what we're interested in seeing in a surface, and we've produced and inspected a step artifact for ITF qualification. Let's measure the ITF of the interferometer. So to my left here, I'll go ahead and change the camera view. To my left, I have a Dynaphys interferometer, and I have the step artifact that we just highlighted in the presentation. And I will switch over to our MX software here, and I'll use that to analyze the ITF artifact once it's measured. So I'll start by aligning the artifact in front of the interferometer. And I can get pretty close, and we have a nice new feature in our MX 8.0 release recently. It's maybe difficult to see, but there's a small picture-in-picture. I have the align mode in a small window here to the bottom right, so there's no need to grab the remote and flick into align mode. It can be done on the same screen, which is a nice feature. So if we align the artifact, we see in fact there are some features etched into the surface there. And back over here into the software, I will make sure my ITF analysis is on. And this interface here is a pre-configured interface for testing ITF that's used in our manufacturing facilities to test ITF of every interferometer that goes out the door. So the only thing to do here, we know that the analysis is turned on. If we hit measure, we'll take a quick phase measurement of the artifact itself. and we get a phase measurement of the surface of the artifact. And what the software is doing is automatically detecting that step edge, both the horizontal and the vertical. And for each edge, it's actually drawing a profile slice, hundreds of profile slices across the step in the horizontal and vertical. And it's analyzing that step in the frequency domain for the amount of spread in the step. And with that information, the ITF can be calculated and is presented here on the screen, both horizontal and vertical. And we see that we get a curve in with frequency, spatial frequency on the x-axis, and the ITF, or the response of the interferometer to that spatial frequency, on the y-axis. And this is normalized to 1, and we can see that indeed, as spatial frequency increases, the response of the interferometer falls off to 0 when it hits the Nyquist limit. So I'll come back here to the presentation. And as we just saw, the step edges are detected automatically. Hundreds of step profiles are drawn. Normalized ITF as a function of spatial frequency is output. And we should note here that performance is most predictable. So we've got this ITF curve, and we'll talk now a little bit about what do we do with that information. It's important to note that the performance is most predictable for ITF above 0.7. And I'll talk a little bit more about that in detail on the coming slides. So let's look at an example. I have here the ITF curves of 3 different interferometers, what we'll call a legacy interferometer. This is something that might have been deployed for the last 10 or 15 years, a 1K camera, incoherent imaging. And the green and the red line are more modern high-resolution interferometers, a verifier HD and a verifier HDX, 2.3K or 3.4K pixel resolution respectively, but we'll talk more about the configurations and what the ITF is for each of those. So as an example, let's say we have an optic, and the spec for the optic is 1 nanometer RMS for mid-spatial frequencies up to, say, 6 cycles per millimeter. So in this case, if we draw a line at the 6 cycles per millimeter mark on our ITF curve, we see that we'll be investigating spatial frequencies that are lower than this. But we can see that the legacy interferometer, the response of the interferometer actually falls nearly to 0 before it gets to the limit of the specification. The other 2 interferometers do have a response that's higher, about 0.7 for the HD and above 0.9 for the HDX. So if we come back and measure our mirror again, if we look at the mirror with the verifier HDX, we see that in this case, the RMS over that spatial frequency band comes in at about 1.37 nanometers. If we look at it with the same mirror with the verifier HD 2.3K, we can see that the surface does look not quite as sharp as it does with the HDX. And indeed, the RMS result reflects that, the RMS coming in at about 1.12. And if we go further and look at that same surface with a legacy interferometer, we see the surface measurement does look quite a bit more blurry than the higher resolution measurements. And in fact, the RMS result over that spatial frequency band is lower. In fact, it's below the spec. So now we've just measured a part that is reported passing. However, it may be because the response of the interferometer just does not allow the spatial frequency information through that would have been important to quantify. So what does one do with this ITF information now that we've seen these examples and understood how interferometers are attenuating surface information? We just saw that any failure to account for ITF in metrology can significantly impact the final product, the mirror or optic being polished. And in optical designs where mid-spatial frequency control is known to be required, there are a few things that one can take account for. First, at a design level, it should be understood that imperfect transfer of mid-spatial frequency content due to ITF will occur, and that can be specified. So if there is an optic with specific control over mid-spatial frequencies, one can specify the ITF of the instrument that would need to that would be required to measure that optic, and knowing that the ITF is a variable in the measurement, that the result of that measurement, the reduced height information, can be accounted for in an error budget at a design level. At a sourcing level, one can define the metrology requirements that meet or exceed ITF specified by the design. And during fabrication, it's important to apply the appropriate metrology to meet the ITF specifications required by the design, and also apply interferometry best practices. So Zygo offers a range of interferometer systems designed with high ITF in mind, starting with the Dynafiz ITF greater than 0.7 up to about 3.3 cycles per millimeter at 1x magnification. The Dynafiz does have a variable optical zoom, which will actually increase that spatial frequency capability, increase the ITF, but at the expense of the aperture size. That's the trade-off with optical zoom. The Verifier HD has an ITF greater than 0.7 at about 5.5 cycles per millimeter. This is the 2.3K pixel camera. And the Verifier HDX, ITF greater than 0.7 at 8.2 cycles per millimeter. And there's a 3.4K pixel camera integrated into that system, and obviously the optical design to take full advantage of that very high pixel density. So each model here is designed with a fully coherent illumination and imaging system for the best ITF performance. That's the goal of these systems. Legacy interferometers with incoherent imaging, they were not designed to achieve this level of ITF performance, regardless of the sensor sampling density, regardless of the camera that's installed. It's really the optical design that determines the ITF. It's not just put a higher pixel density camera in front of the optics. The advantage there will not be realized. The gory details are available in the citations that I mentioned before. If anybody's interested in researching those, they're available on the Zygo website. So just a few final notes here before we sign off. Interferometer image focus is in fact the largest contributor to ITF variability. So even if you have one of these very high resolution, high ITF interferometers, image focus is an important factor to control and optimize even with the high resolution interferometer. And the chart here shows several measurements of the ITF artifact at different focus positions from plus or minus 15 millimeters from optimal. And we can see that at the half Nyquist mark, at the half of the max spatial sampling, the ITF can go from about 0.75 all the way down to 0.4 just because of poor focus. So it's important to ensure that image focus is optimized to optimize ITF performance. The ITF of an interferometer is well defined for plano cavities, but for spherical or more complex cavities, it's much more difficult to qualify ITF. However, models exist and expected performance can be calculated for specific spherical cavities. If there's a need for high ITF, high spatial resolution metrology on non-plano cavities, it's best to contact Zygo and we can try to work through that with you. And ITF as a service. Currently, ITF is only a factory qualification test for new coherent interferometer systems from Zygo. ITF qualification of fielded systems is not currently available. However, we've seen from some of the ITF charts and the examples that legacy interferometers with incoherent illumination or imaging really shouldn't be considered for mid-spatial frequency qualification anyway. And the ITF information or the estimated ITF can be provided for those systems and even the new systems at request if that's needed. So in summary, back to the original question that we started with at the very beginning, how small of a feature can my interferometer resolve? Well, as we saw, the answer is not quite straightforward. And rather than defining the camera pixel size or some other metric of saying what is the resolution of the interferometer, it's really the ITF that's a more complete and meaningful description of interferometer response. And we saw the effects of that as a function of spatial frequency. The useful region of an interferometer's ITF curve is spatial frequencies with a response that is greater than 0.7. So below that threshold, surface information is degraded for higher spatial frequencies, and other means of testing those higher spatial frequencies may be desired. And Zygo offers a range of interferometer products to address mid-spatial frequency needs, as well as a robust method of qualifying ITF performance. So with that, I thank you all for listening and participating. I hope you found this informative. We can pause here for a question or two at the end if there are any.
We do have a couple questions. The first one, can you simply scale up height information at the same rate as the ITF attenuates height information to correct for the effect?
That's a good question. So the answer is that you could do that. However, it's not directly helpful because if you scale up the higher frequency end of the ITF spectrum, you also scale up the noise that's embedded in that information. So the signal to noise ratio, although you've scaled up the height information, the signal to noise ratio remains the same, and so there's no benefit. There's no end benefit in scaling that information up. The best practice is to quantify instrument ITF and account for the imperfect height reporting in an error budget or by specification.
Okay, we've got one more question. Is the ITF dominated by as-built aberrations, or can it be predicted reasonably well based on design?
It can be predicted reasonably well by design. The tolerances of the interferometer system can be input into an optical design, and similar to other optical design metrics, the ITF can be understood over a range of Monte Carlo runs with tolerances included. So at a design level, ITF can certainly be understood. What we went through here was an empirical qualification of ITF of the interferometer, just to back up that theoretical information, and the test actually does agree with the design quite well. So it's another validation that the step artifact and that method of qualifying ITF are quite robust. Good question. All right.
That's it.
Thanks, Mackenzie. If there's no other questions, I'll end it there. And I'll mention here too that if a question didn't get answered, or if there's something we couldn't answer during the webinar, feel free to send questions to inquire@zygo.com. We also have upcoming webinars that are listed on the website, right on the front page under the upcoming events section. And this webinar, as well as previous webinars that have been recorded, are also at zygo.com under the What's New at Zygo channel, right on the front page. You can also check those out on our YouTube channel listed here. So with that, I'll sign off. Thanks everyone for listening and participating. I hope you found it useful, and stay safe and be well, everyone. Take care.